Okay. So in the last class, we had said that, if you consider a set of real numbers and it is said to be bounded if there's another real number h which is greater than or equal to all elements in the set S. So over here, this is the set S. H is the upper boundary if it is greater than or equal to. Here you can see H is strictly greater than, but H can be equal to the maximum element in the set also. So H is called the upper boundary. So we can have many upper boundaries. It is also possible that there is no upper boundary. For instance, if the set is something like this, then it doesn't have an upper boundary. But if you consider a set like this, then we have upper boundary starting from 12 onwards. In case of 12, h is equal to the maximum element, which is 12. This is 12. In that case, h is called the supremum. Okay, but apart from 12, we can have other 13, 14. These are also upper bounds. So if you have one upper bound, you will have multiple upper bounds. And the lowest upper bound is called the supremum. Okay. Similarly, a set of real numbers is said to be bounded below if there is a real number L which is less than or equal to all other elements in the set. Here again you can see that this is small h, but in my notation it is L. L is strictly less than all the elements in the set. But again, just as in the case of the maximum, let us say x is 5. In that case, if we take h equal to 5, we see that it is strictly equal to the minimum of the set. So again, if you have a boundary, lower boundary, you will have many lower boundaries. You will have a collection of lower boundaries, and the highest lower bound is called the infimum. Okay. So if there's an upper boundary, you're going to have many upper boundaries, and the smallest of them is called the supremum. Okay, so you can see that over here, this is the upper bound. This h can be anything starting from b onwards up till infinity, but the maximum, sorry, the minimum of this collection of boundaries is equal to the maximum. Okay. Similarly for the minimum. Now we come to the concept of maximum and minimum of the set.
Sir, can you bring that last to last page back? I was not done noting it down.
This one?
Yes, sir. Just for two
Huh.
minutes.
Yeah, yeah, sure. You have to fill in the gaps, by the way. I've deliberately kept it blank.
Thank you, sir.
Okay. So a set S has a largest element M, capital M, let us suppose. So we can think of a set like this. So this is the maximum element, it is called M. So in that case, M is equal to the supremum. Okay. In other words, if a set is bounded from above, then the maximum of element of the set is equal to the supremum. In this case, what is the maximum element?
12.
No, in this set,
Sir, not
x
defined.
greater than 4.
Not defined.
It's not defined. It
Oh, greater
doesn't
than
have a,
okay, it's not.
yeah. It does not have an upper boundary. Okay. It is not bounded from above. Therefore, there is no supremum. And therefore, we cannot also identify a maximum of the set. Now, if we look at the minimum sets, again, if you go back to this set, this is the minimum. It has a lower boundary. In this case, the minimum is equal to the infimum. On the other hand, if we look at this set, it is not bounded from below. There is no lower bound. And therefore, the minimum is not equal to infimum. In fact, infimum doesn't exist. Neither the minimum nor infimum exists. Okay. In this case, the maximum and supremum does not exist. I think it should be intuitively obvious also.
Sir, what you told, sir? The last statement, what you
I s-
told? Can you tell again?
I said that it should be intuitively obvious to you that unless you have a boundary, the maximum
Yeah.
minimum should. Yeah.
Oh, okay, I got it, sir.
Okay. Now we come to interval. If any two numbers belong to an interval I, then all numbers between x and y will also belong to the interval I. So let us take two numbers, 2 and 4. Okay, so in between we have 2.1, 2.2, and so on. So all these numbers which are between 2 and 4, which satisfy the property all of them belong to the interval I. Okay, so we can write this in mathematical notation that x belongs to an interval I, y also belongs to I, and we define z as lying between x and y. So x can be 2, it starts from 2, it ends at 4. So in that case, z will also belong to I. It will belong to this interval. Okay. Okay. Now intervals can be categorized into
The last page, can you turn once more? So the last line I have missed. Okay, sir. Thank you, sir. I will do so.
yeah. Okay. Now we can divide intervals into several types. We'll come to the graph a little bit later. Suppose we define this as okay. In this case, x cannot be equal to 2 or it cannot be equal to 4. See, what is the importance of 2 and 4? They are the lower bound and upper bound, the infimum and supremum, respectively. Okay. Right? So that means what the value of x starts from, let us say 2.1 and ends at 3.9. Actually, there are more numbers. There are numbers which are closer to 2, but I'm just writing this in short for convenience. So that means we are excluding the boundaries. We are excluding the infimum and supremum. We call this an open interval. And we write this as, we use the first brackets. Okay. So that means the entire interval is there, only the infimum and supremum is dropped from the set. In case of a closed interval, on the other hand, we include the boundaries. So the infimum and supremum which you know is equal to the mean and max of the set, both belong to the interval. Okay. We represent this using square brackets. In both cases, the infimum, the minimum and max, infimum and supremum is 2 and 4, but we have to write a and b within brackets, but the type of bracket that we use indicates whether it is an open interval and or whether it is a closed interval. Similarly, we can have semi-open intervals. Using these 2 and 4, can you tell me what is a semi-open interval? How do we write this one? Square bracket a bracket
Sir,
close.
less or equal to will not be there. There will be less than, and there will be not
So
greater
2,
or equal to. There will be greater
what
than.
will I write? No. What? How
Two
will I write
less,
it? 2.
two less than
2 is less than x and x
x
is less
and
than
x
equal
is
to 4.
less or equal to 4.
Sorry, just a minute.
One side will be open and another side will be closed.
না ইকুয়াল টুটা কোথায় বসবে? এইখানে না
It
এখানে?
can
Equal to
be
left,
two less
left side.
two.
Two less than equals
Square bracket
to
The
x.
means
left, the left side, left side.
The
left
left
side.
side.
Square bracket in the
হ্যাঁ,
left side. A থেকে শুরু
yes,
হচ্ছে left side.
exactly. And over here,
Right
right
side.
side.
it will be on the right hand side. Okay, so we can have open interval, closed, or semi-open. Semi-open can be of two types. So that means if I'm talking about this type of semi-open, I'm including the interval. This is included, but this is
The
the
infimum is
supremum
included, but the supremum is not included.
is not included. Exactly. Unbounded interval. What is the problem over here? There's no lower bound. Okay. So we are just going on like this. So we don't know what is A over here. Right. Over here you can see that when we are talking about the right hand side, it is open. It can also be closed. So we can also think of like this.
Sir, what is the difference between closed interval and compact closed bounded?
Yes, sir.
Closed?
This is also my
Closed
question.
interval and compact closed bounded.
So the last
Yeah,
point,
yeah.
The last
Okay.
one and the second one, are they different?
আমি আসছি এটা sorry, what was I saying? Mm, unbounded intervals. Acha. So if I want to depict this, how do I, what will be the case? It is strictly less than 4. This case. There's no lower bound, and the upper bound, it is open. This one is this one. Okay. Acha.
So,
Yeah, now we come
could
to.
you explain the unbounded intervals again?
Okay. See, for the moment, just ignore the type of bracket, whether it is square or whether it is the first bracket. Okay. See, over here we can see the set is given by x less than 4. So if this is 4, this is not included, but all sets over here are included. Okay. So there is an upper bound, and this upper bound is open. So we know what B is. Okay. But what is A over here? Can we find out what is A?
Not defined, sir.
It is not defined. It does not have any boundaries. It does not have any minimum or infimum. It doesn't have any boundaries, so we say that it is unbounded. In fact, if you want to be more precise, it is unbounded below. So if we don't include 4, it is unbounded from below. We write it as x less than 4. X can be 3, it can be 2, it can be -1 up till infinity. If we write it at x less than equal to 4, then we are also including 4. Okay.
Yes, sir.
Okay. Similarly, we can also define a set which does not have any upper boundary. It only has a lower boundary. So how do we write it? Can you give an example?
So x is greater than 2.
Yes. So here the lower boundary is open. But if you put in a greater than equal to, it is a closed lower boundary. But in both of the sets, we don't have an upper bound. So the set will be, this is 2, and it will just go on like this.
Excuse me, sir.
Yes.
Sir, so in these cases, can we write maybe 2 is less than equal to s, which is less than infinity?
Yeah, you can write it in this way, but I mean, why bring in addition? I mean, what you're saying is that we write it like this. No, I'm writing this one. You mean like this? It
Yes,
doesn't
sir.
have a lower bound. I mean, why bring in this? This is much more concise, isn't it? It
Yes,
implies
sir.
this.
Yes, sir. Yes, sir.
That's one.
Okay, sir. Thank you, sir.
Yeah. Okay, compact interval is that it is closed. So that means the boundaries are included and you have boundaries. Yeah, I mean, in that, yeah, you're right that a closed interval itself is compact, but what it basically implies is that you have both the boundaries exist. Both the boundaries exist, the boundaries are included in the interval. So yeah, I mean, closed and compact. Just 1 second, please. Okay. Okay, I'll answer your question, but I'll have to remove the writings. So if you want to copy anything, please copy it and I'll delete the writings. And then I'll explain what is compact.
Sir,
Yeah.
sir, this PDF, the one you are like showing us the slides, sir, could you send us in the form of documents?
1 second. Okay, Nasir. হ্যাঁ 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 না না ঠিক আছে Okay. Sorry, I got distracted. What was your question?
Sir, like
Oh,
the
okay. You were saying
slides,
that you want the slides.
Yes, sir. The slides you're showing, can you send us in the form of documents or PDF?
Mm, you mean with the writings?
No, sir. Without the writings is also okay. Just the main stuffs out there.
See, I can send it to you for the first part, for the first module, the basic concepts.
Yes, sir.
But subsequently, what we have found is that I mean, students tend to just write. If I ask you what is a semi-open interval, you'll just write the square bracket. You won't explain anything. So that is why we don't generally send out the slides. And people say that okay, you have just written the square brackets, but this is not the definition of a semi-open interval. Okay, I'll send it to you for the basic concepts.
Yes,
But
sir.
subsequently, if you want to, I'll give you time to copy it out. But I won't send the slides from the second module onwards. Okay.
Yes, sir.
So everyone has copied this, the writing.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. So suppose the interval is unbounded. Okay, we have bounded intervals. Or better still, let's think of it. We can make a table like this. Bounds. Okay, so if it is bounded, if there are bounds, we say it is bounded. Okay. If there are no bounds, it is unbounded. Right. Acha. Now, are the bounds included? If it is yes, then it is this. If the bounds are not included, it becomes open. Okay. So this is a compact set. Let me explain this, that if you have an unbounded interval, okay, I'm just talking about the lower boundary. Okay. So we write this as this is open to. So as you have correctly said, we have to put in the minus. Okay, minus infinity. So we put in square over here. But because it is unbounded, we see that it is going on to minus infinity and we keep it open. Okay, so this set doesn't have any boundaries, but these are open. This is open. And this is semi-open or half open. So you have to have, in order to be compact, you have to have boundaries. That is, you have to have A and B. And secondly, in both points, they have to be closed. So in that sense, you can see there's not much difference between a compact interval. I mean, theoretically, it's possible.
I
If you look
couldn't
at this table,
understand
it's
it properly.
no, I haven't finished. It's not possible to have this type cannot exist. Okay, unbounded and closed. So in that case, compact and closed will be. You're right. Compact and closed are basically synonymous. If you just say that it is closed, then that will be sufficient. But the strict definition is that it's closed and bounded. But as you can, if you think intuitively, you cannot have a closed set which doesn't have any boundaries.
Sir, closed set without any boundaries, sir. How can it happen? I mean, sir, whenever we are writing,
Now
sir,
that
in
is
the
what I'm
last
saying.
diagram.
হ্যাঁ বলো
Oh, acha. Now, actually, sir, in the last diagram, here it is written, sir, from A to infinity, but while the infinity is not touching the infinity, so it is
no
unbounded only, na? So,
হ্যাঁ that is what I'm saying. A closed set has to have boundaries.
yes, sir.
Okay.
So the result of the compact and closed interval might be same, but the definitions are a bit different, right?
Yes. হ্যাঁ
Oh, okay, sir.
we cannot
Okay, sir.
have a
Got it.
closed set which does not have boundaries.
Okay, so now I
And unless
understood,
you
sir.
have a boundary, how can you include it within the set?
Exactly, sir. Exactly.
Okay. So what are natural or whole numbers? The set is, and there is strictly positive, and we are not including the decimals. Okay. Okay. So assume that okay. Anyway, this is not necessary. So we define x is okay. Now, as you can see from the set, x is strictly greater than 0, right? X starts from 1, so it is strictly greater than 0 by definition of natural numbers. Okay. So 0 is the lower bound. Okay. Now suppose you can have other lower bounds also. B is the largest of the lower bounds. Okay. So if B is the largest lower bound, is it possible for B plus 1 to be a lower bound?
No, sir. B is the infimum also, no? If it is the largest lower bound.
It is the infimum. So if I
Yeah,
add
yeah.
1, it will immediately become 1 or greater than 1.
Yeah,
এই সেটের মধ্যে লাই করবে।
exactly, sir.
I'm starting in from 1. So that means if I'm adding 1, it will come over somewhere over here. Sorry, actually my hand is okay. So that means B plus 1 is not a lower bound. Okay. So let us take n less than b plus 1. Okay, now we can have the following possibilities. Now suppose n is the minimum of S. Okay, in that case, automatically we have proved it. This set of natural numbers has a minimum. Okay, so if you are defining something n less than b plus 1, this n can be within this set. It's possible. So if n is
Yes,
within the
sir.
set, it is the minimum, so there's nothing to prove. Achha. The other thing is,
But sir, what is the definition of n? মানে from assumption by anything?
now n is a number which is less than b plus 1.
Any natural number?
Hmm.
Okay.
Achha. Okay. If this is not true, n is not the minimum of S, then this is the second possibility. We have some m which belongs to S, for which we have m less than n. N is not the minimum. Okay. So that means there must be some other part which is lower than m.
Yes, sir.
Okay. So in that case, we have see n is less than b plus 1. I've written this. M is less than n. So this. And b is the largest upper bound. So m has to be, cannot be less than b. It can be either greater than b or it will be equal to b. Okay. So if we manipulate this, n minus b,
So could you explain this part once more?
last line টা
Yes, sir.
হ্যাঁ এটা আমি এক্সপ্লেন করিনি, আমি জাস্ট লিখলাম। আচ্ছা, we are using this relation. Okay. ঠিক আছে, so I'm deducting m from here. Okay. Now m is not equal to m. N is greater than m. ঠিক আছে, so this has to be greater than 0. আচ্ছা, এইটা হচ্ছে কি, আমি m বাদ দিচ্ছি। Okay. If we look at b and m, কিভাবে করছি? b plus 1 m minus b যদি আমি, আচ্ছা এ, ও সরি, এটা এইভাবে হয়ে যাবে। এইটা আমরা লিখলাম, তো এটাকে আমি একটু আলাদা করে লিখছি, b minus m plus 1। আচ্ছা, b minus m টা কি, ইকুয়াল টু হলে এটা 0 হবে, আর আদারওয়াইজ দিস উইল বি নেগেটিভ, তাই না? Wait a minute. So this term will be either 0 or it will be negative.
So can
Just one second. 1 second, please. Please give me 2-3 minutes, please. I'll come back now.
okay, sir.
Yes, sorry. Yeah, just let me just have a
Sir,
look up.
sir,
Bolo.
here it is given that n is less than b plus 1. Then if we subtract n from both the sides, then it will be n minus m is less than b plus 1 minus m. Again, m is greater than equal to b. Therefore, n minus m will be less than b plus 1 minus b. So, n minus m will be less than 1. Then that part will come.
Okay, so you have solved it yourself.
Yes, sir. And 0 is less than n minus m, that is given from m is less than n. From
Yeah,
what we
0 to
mentioned. Yes, that's what.
yeah. Okay. So if you get this, so this statement implies that n is not the minimum. Okay, so in that case, we get a term like this. What is n minus m? Okay, but n minus m, both of them are natural numbers. Okay, so if you're talking about the division, I mean, if you take the numbers, uh, what will be the minimum gap? The minimum gap has to be equal to 1. If you take 2 and 1, the gap is 1. 3 and 2, it is 1. But if you take 1 and 3, it is more than 1. So the difference between any two natural numbers is either greater than 1 or it is equal to 1. Okay. Just look at the set of numbers and remember that both n and m are natural numbers. So if you take n minus m, it cannot be 0.5. It can be 1, it can be 2, it can be 3, it can be something like that. Another natural number which is greater than 1. But here we are seeing that n minus m, so this is because n and m are both natural numbers. But here we are seeing that n minus m is less than 1. This cannot be true. So if this cannot be true, then this part, this entire logic breaks down. And so we only have this possibility. N is the minimum of S. Okay.
Sir,
Bolo.
sir, here I want to just ask one thing that in exam this proof will be proofs can be asked.
Yes, we can ask you to prove it. Why?
No, just asking.
Proof জিজ্ঞেস করা যেতেই পারে। Okay, now this is another problem. Suppose there's a man, I remember that one of my colleagues told me this story. many years ago, in 1995, we were traveling by train to our college where we were teaching, and he told me this story. So, when we were returning home, so the story is sorry. There's there's a man. It can be Bolt. It can be someone else, and that man runs at a speed of x. The dog runs at a speed of 2x. So they start running in a field. So this is a straight field, and they start running. The man is over here, and well, I can't draw the dog. So this is the dog, and both of them start run, and they reach over here, and after obviously the dog will reach earlier, and then the dog runs back like this. So the dog, both of them start like this. The dog reaches over here, and then the dog comes back and meets the man. Suppose the man is here. As soon as he meets him, he runs back over here, goes to the boundary, and then again comes back. So the man is going on like this. The dog is running back and forth. And this goes on till the man reaches this side of the field. Okay, so this is a straight line. The question is, how much has the dog run? Let us suppose that the length of the field is 200 meters. The speed of x is, he runs, let's make it 2 kilometers, 2000. So he runs 10 meters in, sorry, not 10 meters. He runs 2 meters in a second. So this is 4 meters per second. Okay, you don't have to solve it, but how will you solve the problem? Have you understood the problem?
Sir, not much, but both are starting to run from the same point, right?
Yeah, they're starting
Now,
from here.
yeah,
The man,
the dog is reaching the end and again coming back to the man.
yes.
Sir, I guess the dog runs 300 meters the first time, and then in the subsequent trials, he runs half the distance every time. So I think we sum those up.
Okay, very good. So what you're doing is, you're developing a GP series, right? You're
Yes,
suggesting
sir.
that we look at the problem as a convergent GP series. The dog is running, let us say, theta. The next part, it is slightly less than theta, some fraction of theta.
Sir, how it is becoming GP series? Can you explain a bit?
Yeah, let your friend explain.
Okay, sir.
Okay, so the first time the dog runs 200 meters to the end of the field, and the man runs half the field. He runs to 100 meter, and by the time the dog comes back, so the dog runs total 300 meters. Then they start running again. So the man covers 50 meters, 100 meters, but no, the man covers 50 meters, but the dog covers three times of that. But since they're covering half the field only this time, so the total distance the dog has covered would be half. Subsequently, the distance covered by the dog becomes half every time he comes back to the man. So it becomes a GP series where the common difference is half. We sum the GP then.
Okay,
Did
so
you get it? The GP.
Yeah, so actually what happened was that this problem was given to mathematicians and physicists. So when it was given to mathematicians, they set up the problem like this. The dog has run 200, actually it's 2 kilometers, not 200, but anyway, he has run 2,000 meters. By that time, he has run 1,000 meters. So now they have to come back like this. Okay. So it's a steadily decreasing series. A sequence is formed in which the distance that the dog has to run is gets gradually reduced. So we form a sequence x. I'm just giving x by 2, something like that, and then you just sum up the GP series, which you have done in your class 12 level, I think. But when the problem was posed before the physicists, it was found that they solved the problem much faster than mathematicians. So they were asked that how did you solve it? I mean, the mathematicians, see, I mean, you're not so expert in maths. I mean, this question was asked not to a mathematics student, but to very famous persons in mathematics, very great mathematicians. So they are able to set up a problem and solve it much faster than you can. So it was found that I think mathematicians took about 9 to 10 seconds to solve it, but the physicists took 5 seconds to solve it. So this is surprising because mathematicians are supposed to be better in solving this type of problem. So they were asked that how do you solve it? So they said it's very simple. See, how much has the man run? How much has the man walked or run? He has traveled, the man has traveled 2,000 meters, right? The distance from here to here is 2,000. What is the speed of the dog?
That 4 meters per second.
Double that of the man. So in the
Yes, sir.
same time, how much will the dog have traveled?
The double distance.
Double the man's distance. So it is
Exactly, sir.
simply 4 kilometers. So you don't really, you can solve it using a GP. It's perfectly conceptually correct, but you can also solve it logically also. So the physicists were able to solve it faster than the mathematicians. But with one example. This
But
is
sir, the
this.
thing of GPI can't understand yet.
It doesn't matter. Kanami GP, it's not a problem that you have to solve. What I'm saying
Okay,
is
sir.
that only one person, only one mathematician solved the problem in 5 seconds. You won't recognize him now, but you'll be reading a great deal of his works from the second year onwards. This
Sir,
person
who is
solved.
he?
Yeah, this is Johnny von Neumann. John
Oh.
von Neumann. We will read his works on game theory from the second year onwards. In fact, partly from the next semester also. Neumann and Morgenstern, they wrote the first book on game theory. So the people who were conducting the experiment said that this is a mathematician who thinks like a physicist when they refer to John Neumann. So this is not a part of your course. This is just a story, a true story, but nevertheless it's a story. I just wanted to break the monotony, and I mean it gets very boring. So I wanted to break the monotony. And plus, I think you should also know about a little bit about the different people and the history of the different sciences. Okay. Now, the reason why I wanted to discuss this was that I'm now going to introduce the concept of sequences. Sequences, convergent sequences, and so on. Okay. Okay. Now, the first thing is, what is a sequence? Well, primarily it is a list of numbers x1, x2, x3, so on, that are determined by some rule. Okay. So what is this rule? We have a set of natural numbers and these natural numbers are, let us say, n. So the natural numbers are 1, 2, 3, 4, so on. And each natural number n is assigned a unique real value which we call xn. Okay, let me give an example that will make it clearer. Consider a rule xn is equal to n plus 1. Okay. So what does it mean? We start n from, what is the starting value of n? 1. So if n is equal to 1, what is the value of xn? It's 2. If n is 2, what is xn? It is 3. Right? So the set that we are talking about, the list of numbers, let us call this t. Then actually problem ho jai. So this t is right. Can you suggest any other any other rule?
So 2n minus 1.
Yes, I didn't get you.
So I could say 2n minus 1.
Oh, 2n. Okay, so this will be n is 1, it is 2. কত হচ্ছে তাহলে এটা 1 হচ্ছে। So this is 4, it is equal to 3. এটা কত হচ্ছে 6, it is equal to 5. So now what is t? 1, 3, 5, so on. We can think of it in this way. These are all different types of rules. এটাকে আমি 6 করে দিচ্ছি, এটাকে আমি 2 করছি। You can think of many rules, and in this way you can form different types of sequences. Okay, and we write a sequence like this. It is use the greater than equal to sign instead of the square bracket or whatever. So this implies a sequence whose nth term is xn. So the set of all this is called the range of the sequence. So we know where the sequence starts, where the sequence ends. Now obviously, again, the range of the sequence it can be bounded above or below. So suppose we say that n is defined as less than equal to 10. So that means when we are going on like this, n can go at the most up till 10. So that means we are setting a limit to, because we are setting a limit on n, xn also has a limit or bound. In this case, it has a lower bound. Sorry, it has an upper bound. It is, what is the lower bound? The lower bound will obviously be 1, but we can also a lower bound will always exist because n cannot be less than 1, but we can also set other lower bounds. For instance, if I say this, in that case, the lower bound of n is 4, and this means that xn will have a corresponding lower bound for n equal to 4. a sequence is said to be form a convergent sequence only if the following property is satisfied. Wait a minute. Sorry, A type 2. Okay. Okay, so we have a sequence whose value is I think it's better understood if you think of a think of it in graphical terms. We assume that it's an increasing sequence. What we can see is that when the value of n is going up, xn is also rising. Okay. Now we see that it will converge if you find some capital N such that for any n which is greater than n, okay, this so we are taking a particular value and we are looking at this gap. Okay. Why I'm taking modulus? The reason is that it can also be a decreasing function. Okay. So xn minus L, the gap will be always.
So it is E or epsilon?
It is actually epsilon,
Okay.
but my writing is not very good. So you have a positive epsilon, and this gap will always be less than this positive epsilon. So in other words, what you're seeing that as you're approaching, there will always be a gap. Okay. So in this case, we can see that xn minus L, L is greater so that is why we are taking modulus over here. We can also think of a gap, a situation like this, where it is coming down. I'm ইচ্ছে করে একটু ওপরে নিচ্ছি. I'm taking it a larger.
Epsilon greater than 0, right?
Epsilon is greater than 0. So basically what I'm saying is that xn will never be equal to 0. There will always be some gap. And the gap is less than this small value, epsilon.
Sir, আরেকবার বলুন, মানে just tell it once more, sir. Actually, I can't understand this part.
এটা গ্রাফিক্যালি দেখো. Forget about a
Sir, second
direction.
graph টা? Second
না
graph.
প্রথমে ফার্স্ট গ্রাফটা দেখো। ডোন্ট লুক এট,
হ্যাঁ স্যার।
ডোন্ট থিঙ্ক অ্যাবাউট xn মাইনাস এল, থিঙ্ক অফ ইট অ্যাজ আ ডিফারেন্স, ঠিক আছে?
হুম।
So look at the gap between L and xn. What I'm saying
Yes,
is
sir.
that it will always be less than a certain value,
Okay, sir.
which is positive. এখানেও দেখো, it is always less than a certain positive value.
Okay, sir. হ্যাঁ স্যার, বুঝলাম।
আচ্ছা, মানে you're not, basically what we are saying is it is not going to touch it like this.
Okay.
Oh.
Sir, what is L? Is L the limit?
Yeah, I'm coming to that immediately. এরকম এই জিনিসটা এখানে if you look at it, at this point xn minus L becomes 0. But
আচ্ছা,
we know that
it is not gonna happen.
epsilon is greater than 0. So
Yes,
this
sir.
point is not satisfying.
Oh, okay, sir.
So this is a decreasing function. So this part is okay. We cannot come over here. If you look at the positive part, touch here again,
0 হয়ে যাবে।
0 হয়ে যাচ্ছে। So again this is not possible.
Yes, sir.
So what we see is now we are defining in terms of limit xn tends to L as n tends to infinity. Yes. Or if I want to write it as in limit form, so the limit is L. I will not reach it, but I'll come close to it.
Okay, sir.
I'm going to approach it, but I will never reach it.
মানে ওটা ইকুয়াল হবে না।
Equal hole, I've reached it already, and
Exactly.
xn minus L becomes 0.
Yes, sir.
So if you look at this part, this is the textual statement. But if you look at it graphically, and if you look at the limit definition, then it becomes the definition of convergence becomes clearer. So if you have to write it, you should, or you're asked to define it, you should use this part. But for understanding graphs, and this part is easier.
So what did you actually prove from this?
I'm not proving
The
anything,
whole
I'm
thing
defining.
is-
This is a definition. মানে here I've said that we have a sequence of numbers. Now the sequence can be, when is the sequence convergent? Why are we focusing so much on convergence? Because in that case it is
Sorry, my
possible.
connection got lost.
Okay, no, it's okay.
Yes, sir, I was asking that from these graphs and diagrams, so like what did
Oh,
you
11
actually
অব্দি এদের না?
explain that?
Oh, sorry. আচ্ছা। হ্যাঁ সরি, তুমি কি বললে? সরি,
So I
কি
was
বললে
asking
তুমি?
that from this graph and this. Sir, you asking me?
না, তোমার কথাটা না একটু কেটে যাচ্ছে। হ্যাঁ, গ্রাফ থেকে আমরা কি করছি?
Exactly, like what are we trying to do from this graph?
আচ্ছা, আমরা যে সিকোয়েন্স, কনভার্জেন্স সিকোয়েন্স কাকে বলে সেটা ডিফাইন করছি। We are trying to define what is a convergent sequence. So we are saying that we have a boundary over here, you approach it, but you never touch it. That is what I'm trying to say.
Oh, because if we touch it, it becomes 0.
Yes, yes,
Right.
yes. So basically, intuitively, you can think of it. Uh, if you look at this xn minus L, as n increases, you're going to approach L. So the gap between xn and L is going to decrease, but it will never be 0. মানে
So that means we approach towards that L, but we never touch it. That is the limit
yes,
part.
হ্যাঁ, এইটা তোমার L হলো। Look at this graph. আমরা যখন এইখানটা নিচ্ছি, what is the gap? This is the gap. এখানে নিচ্ছি, this is the gap. So you can see that the gap is coming down. Gap is coming down, but it is, sorry, never equal to 0. It is only approaching 0. Here also you can see that the gap is coming down. Gap is becoming smaller and smaller. But again, the gap is only tending towards 0. It is never equal to 0. Okay, so I'm ending at this point because I've overstepped my time. If you have any queries, just go through the slide again,
Sir,
and if you still
sir.
have queries, I'll discuss. হ্যাঁ,
Sir, could you repeat this next class again?
হ্যাঁ হ্যাঁ করে দেবো আমি। এখান থেকে আমি এই লাস্ট 3টে স্লাইড আবার করাবো।
Thank you, sir.
ওকে, আচ্ছা, এমডি যেটা বলেছে 11:25 এ স্টার্ট করবে। ওকে,
Thank you, sir.
yeah.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.